Kinetics, chemical kinetics. Okay. So what is chemical kinetics? So chemical kinetics is it's an area of physical chemistry. So chemical kinetics really deals with the rate of chemical reactions. So how fast do chemical reactions go? And it turns out that if we analyze the rate of a chemical reaction, how fast it goes, we can learn something about the mechanism of the reaction. So basically, what reacts with what in what order to produce what, okay? So the mechanism of the reaction. So this is how the reaction goes forward. So how do the chemicals interact? So what order do they interact in? And yeah. And also, we might even be able to learn something about the transition states or the intermediates. So when a chemical reaction happens, you have reactants going to products, but you might have some stuff in between. So these would be called intermediates. Additionally, when two or three molecules collide with each other, or something like that, while they move from our reactants to our products, there's there's a thing in the middle, a very short-lived, how would you say, like a very short-lived state, which is called the transition state. So analyzing the rate of chemical reactions can give us some insight into these. Okay. So how does a chemical reaction happen? So fundamentally, chemical reactions happen when particles collide. So I have a picture of like demolition derby. So we have a bunch of cars going around colliding with each other, okay? So chemical reactions happen when particles collide. And this collision will result in some kind of chemical transformation. So you go from like your reactants to your products or maybe intermediates or something like that. It doesn't really matter. So there are two important factors for a successful chemical collision. So the collision should happen in the right orientation. So, you know, molecules have lots of different atoms. So you need the right atoms to collide with the right atoms. So the molecules need to be positioned correctly. Additionally, these collisions need to have a certain amount of energy. Otherwise, the molecules will simply bounce off each other. So these collisions would be called elastic collisions because the same amount of energy goes in as goes out. So if there's not enough energy, in other words, if the particles are not moving fast enough, nothing will happen. They'll just bounce off each other, okay? So what are the factors that impact reaction rates? So first of all, we have the nature of the reactants. So the size of the reactants, the shape of the reactants, all will influence whether a collision's orientation is going to be good. So if you have like a very large reactant, so with a lot of stuff in it, it might block another molecule from colliding correctly, which would be called like steric bulk. So the nature of the reactants. And you also want to consider the bonds being formed and the bonds being broken. So for example, like if we have a reaction between ions in aqueous solution, so these ions can sometimes easily interact with each other. However, for like the decomposition of hydrogen peroxide, for example, you might need to break some might need to break some bonds. So it takes energy to break these bonds. So, and you need to have a lot of collisions with enough energy. So another example, so in an aqueous solution, if a cation and an anion react with each other, because they have opposite charges, so they interact with each other very favorably, they attract each other. So often those kinds of reactions can be very fast. But reactions between cations or reactions between two anions, because there's some degree of repulsion, so sometimes maybe those reactions will be a little slower. Okay. What about reactions in the solid phase? Okay. So if you have a greater surface area, the reaction will happen faster since there's simply more sites for collisions to happen. Collisions can't happen on the interior of a solid, but they can definitely happen on the surface. So, if you've ever tried to like light a piece of coal on fire, it's very difficult to light a piece of coal on fire. However, in the coal mines, they would have coal dust, and this dust has a very high surface area. So this dust will mix with the oxygen in the air, and it will react very, very quickly if there's an ignition source. So these would be so you could cause coal mine explosions from a material that's not usually flammable. Another good example would be flour. So bulk flour is very difficult to light on fire, but if you can get flour suspended in the air, you've greatly increased the surface area. So very powdery light flour floating in the air is actually very, very flammable. Okay. Another important one is concentrations. So remember in the last lecture, we talked about some different units of concentrations. So if we have a very high concentration, we have more molecules in a given amount of volume, right? Because concentrations are basically just how much stuff you have per unit volume. So if we have more stuff per volume, that means we're packing more particles into smaller space. And so just like a crowded subway, there are just more collisions, right? So if you have more collisions, it's more likely that at least one of them is going to be successful. So higher concentrations will lead to higher reaction rates. Also, temperature matters important. Temperature is important because so basically the distribution of particle speeds follows like this this curve. So somewhat like the Maxwell-Boltzmann distribution. So it's like a curve. So as the temperature increases, the curve starts shifting over to higher velocities. So as the temperature increases, your particles start to move faster. So this means that at a higher temperature, a larger fraction of the molecules in your sample will have enough energy to have a successful chemical collision. Okay? So higher temperature will result in higher reaction rates. So, if you put something in the oven at 500, and if you put something in the oven at 350, the one at 500 is going to cook faster, right? Okay. Additionally, we have catalysts. So catalysts will often work by providing a different reaction mechanism. So, imagine you're trying to get from place A to place B, and there's a really big hill in between them. So you can't really bike very fast between place A and place B. But a catalyst might work by, for example, just digging a trench between in the hill between place A and B, or building a tunnel. So it provides you a different way to get from place A to B that requires less energy. And because it requires less energy, more of the collisions will have enough energy to make the reaction go. So I've been talking about this energy that the collisions need to have. So we can think of this as activation energy. So given by the symbol capital E with a lowercase with the subscript A. So here we can see we have the energy of the system. So it's called free energy. And we'll talk more about this when we do thermodynamics. But you can see that the energy will increase because in the molecules, when you push them together, they will repel each other at first. But then we go to the products. So the products will have lower energy than the peak. So the peak is called the transition state. So here we have the transition state, a very high energy, short-lived thing. So you can see when we have a catalyst, the catalyst will often lower the activation energy. And because we have a lower activation energy, the particles don't need to have as much energy during the collision. So the reaction goes faster. So I want to generalize. So how do we quantify this stuff? So we quantify this using rate laws. So mathematical rules that describe the reaction rate. So here, I'm just going to give you a generalized sense of these rate laws. So basically, in its most basic sense, reaction rates are proportional to reactant concentrations or pressures or whatever unit you're using. So we have here the law of mass action. So I have here an example reaction. So sum A plus sum B plus sum C, et cetera, goes to products. And the products don't really matter when we consider the reaction rate, at least for now. So the rate is equal to some constant K times the concentration of A. So an A in square brackets means the concentration of A raised to some power times the concentration of B raised to some power and times the concentration of C raised to another power. So notice I've used alpha, beta, and gamma here. So I want you to make this very clear. A is different. This alpha is different from A. So these coefficients here have nothing to do with the overall rate law, which is a common misconception. So if we want to determine these exponents, A, B, alpha, beta, and gamma, we need to use experimental data, okay? Only experimental data will do. Or we can look at the mechanism, but the mechanism is often determined by experimental data, so yeah. So alpha, beta, and gamma are unrelated to A, B, and C. So notice this K is lowercase. You cannot use a capital K. It has to be a lowercase k. And it's the rate constant, and it remains constant through the reaction. It's a constant. And the only thing that really changes K is temperature. So, you know, as the temperature increases, the reaction rate will increase. So as temperature increases, the K will increase. K will increase. So the sum of alpha, beta, and gamma, so our exponents, is called the reaction order, okay? So if A was 1, B was 1, and gamma was 2, so 1 plus 1 plus 2 is 4, so we would call it fourth order. Or if A was 0, B is 0, gamma is 0, it's 0th order. So 0 order, first order, second order, etc. And your rate will be in units of moles per second or moles per liter per second. Moles per liter per second, probably the most common, or maybe like atmospheres per second if you're talking about gases. So the rate constant often has very funny units because you need the units to work out so that you get the correct units for the rate. So if you know the units for the rate and you know the reaction order, you can easily derive the units for the rate constant. What was I going to say? Also, if you look at two reactions, it can be very difficult to compare rate constants because the reaction order may differ. So yeah, that can be very difficult. So often it's not a really good idea to compare reaction rates just solely based on rate constants. So the higher order reactions tend to have very small rate constants because you're multiplying it by a lot of numbers. But yeah, that's minor side note. Okay, so this is the generalized rate law. So all by themselves, these don't really tell us much. Oh, did everyone record down the law of mass action? Okay. So, so these rate laws don't really tell us too much. They only tell us the rate. They don't tell us how much in total. So basically, if you were to graph the concentration versus time, the rate law can tell you the slope, but it can't tell you the area under the curve. And when you learn, so we have to turn to calculus to actually get some use out of these rate laws. So you don't need to learn the calculus, just write these rate laws down, okay? So these we call the integrated form of the rate law. So the derivation comes from calculus, so it's integration. So I want you to consider, so first we're gonna consider a zero order reaction. So the reaction of reactants R goes to products P. Then, therefore, we can write that the rate is equal to the rate constant times the concentration of R to the 0 power. In other words, this is just K, right? Anything to the 0 power is 1. Hence, the rate will be a constant. And if we graph R, the concentration of R over time, concentration of R versus time, we should get a very simple line where the slope is equal to negative K, because of course it's decreasing, right? Yeah, because the reactant is getting consumed, so the slope will be negative. Okay? So the integrated form of the zero order rate law is this. So the concentration of R at some time t equals the initial concentration of R, which we call R0, minus the rate constant times t. Oh, I made another typo. Let me fix that. This should be P. And likewise, so this basically just says we start with some amount of R and then KTR. So K times T is going to get consumed. So if K times T gets consumed, then we're going to produce K times T products. So therefore, the product at some arbitrary time equals the initial amount of product plus the rate constant times time. Okay, so does everyone understand what these symbols mean? Right, so this stands for the concentration of P at time t, and this stands for the concentration of P at time 0, so the initial concentration. Likewise, this stands for the concentration of reactant at time t at some arbitrary time, and this stands for the concentration of reactant at time 0. So yeah, so initial concentration. So let's just do a problem. So I'll give you a few minutes to do this. So suppose we have a initial reactant concentration of 1 molar. So I forgot to write the 0, but this is initial concentration. So we have an initial concentration of 1 molar and an initial product concentration of 0.1 molar. We have K equals 0.05 moles per minute. So how much R and how much P will there be after 10 minutes? So I'll give you a minute to do this. Do you have any numbers? Yep. So do we have any solutions yet? No? Okay. Well, let's look at the data I've given. So we're given that R0 equals 1 molar. What else? And then okay. So yep, great. So I think that's correct. So of course we just need to plug stuff into the equation. So R0 equals 1 molar P0. So we just do R of T equals right, and that's fairly easy to evaluate. And then the same, oh, that should be minus, my bad. And then of course it's the opposite for the products. Okay. So everyone has a calculator, right? A scientific calculator. You should have a scientific, it's probably best to have a scientific calculator with you, by the way. Oh, okay, here's the next slide. So now we can talk about the first order rate law, which is slightly more complicated. So again, we have some reactant A goes to some product P, where rate equals K times A to the first, so just K times A. So can someone tell me what the units for K should be in this case? What do you think the units should be for the rate constant? So we need rate to be in units of moles per molarity per time. So molar per time or something like that. So therefore, K should be inverse time. So we have inverse time times some concentration, which gives us the correct units for rate. Okay. So as you might imagine, as A starts to decrease, the rate also will decrease because the reaction rate is constantly changing, which makes this one a bit more difficult. So as you can see, if we graph A over time, A versus time, so A versus time here, you can see it follows a curve, right? Where the slope is equal to K times A. Okay, so using a little bit of calculus, we can come up with the integrated rate law. And here it is, here. So these two rate laws. And what I want you to see is that we can use some logarithm rules. Oh, wait, I made a really bad typo here. Let me fix that. That should be A, and that should be P. Does everyone see the thing I fixed? So this should be an A. Right. A. And this should be a P. So can you copy those down? Okay. Now what I want you to notice is that we can use some logarithm rules. So we start with ln of Therefore, we have right? So we can come up with this equation. And I want you to notice that we have a ratio here. We have a ratio here. So that means that for a first order reaction, the ratio between the things at different times will be constant. So what this can tell us is, so let's say, have you ever heard of half-life? Half-life? So this is basically how long does it take for the concentration to become half of the initial. So therefore, we can plug in 2 and 1 because 1 is half of 2. So we get kT, and then where T1/2 is the half-life, equals natural log of 2. So therefore, T of half-life equals ln of 2 over K. And likewise, K equals ln of 2 over T1/2. T1/2. So as you can see, so we have half-life is a constant, where T1/2 is ln 2 over K. Okay? So additionally, so all nuclear reactions, so your nuclear decays, so like your uranium decaying, those are all going to be first order reactions. So nuclear radioactivity has a constant half-life, which is measurable. Okay? So this is very useful for radioactive dating. So we can measure the radioactivity of different substances, and then we can compare it to a known value for the initial radioactivity. And since the half-life is a constant, we can easily calculate the time. Okay? So this is the basis behind radioactive dating. So radiocarbon dating, and uranium, or your other stuff. Okay? So suppose we have, so I want you to do this problem. So suppose we have A equals, initial concentration of A equals 3 molar, and initial concentration of P equals 0.2 molar. How long does it take for A to become 1.5 molar? And how much P will be present after 30 minutes? And here's the value of K. So I'll give you another minute to do that. So make sure to post the answer in the chat if you have. Be ignored. So basically, yeah, I don't know what I was thinking when I was doing this. So basically what you need to do is you need to find the change in products. So you need to find the change in reactants, right? So you need to find the change in reactants, and then you can and then the change in reactant, and then the change in products should depend on the change in reactants. You can calculate it from that. But on the previous slide, both equations are legitimate because the reaction rate is a constant. It doesn't depend on the concentration of reactants. Okay, so I'll just do this. Yeah, my bad. So the first thing I want you to notice is that 1.5 is half of 3. So how long does it take for the concentration of A to halve? So we want the half-life. So can someone tell me the half-life? So what's the formula for half-life? Just use that. So natural log of 2 divided by k is 5.64 minutes. So it will take 5.64 minutes for the concentration of A to halve. Now let's do the first part. No, let's do the second part. So how much product will be present after 30 minutes? So let's go over here. Nope, camera. Okay, so more. Oh, I'm running out of paper. Okay. So we have that ln of right? Now, just to save you an extra step, what we're going to do is we're going to raise both sides to the e power. And then, can someone tell me what this side becomes? AT. Perfect, because that's exactly what we want. And then this equals does everyone agree with this statement? Okay. And then obviously this just becomes A0. So therefore we have AT equals A0 times e to the negative KT. And then I think you can just plug that in to get the concentration of A at time t. So let's do that. So it equals okay, so we have the final concentration is 7.49 times 10 to the minus 2. Therefore, we can calculate a change in concentration. So delta A is the change in concentration of A equals 3 minus 7.49 times 10 to the minus 2 equals 3 minus equals 2.93. Now, so now we have the change in A, and now we look at our reaction equation. As you can see, for every mole of A that we consume, we produce 1 mole of P. Therefore, delta P equals negative delta. Oh, this should be negative, my bad. Right? Oh, no, this should, yeah, I messed up the sign. So it is negative delta A. Of course, if you're doing a problem out and you mess up the signs, don't worry about it because just use some common sense to straighten it out, okay? So because A is decreasing, the concentration of A is decreasing, our delta A should be negative. So yeah. So delta P equals negative delta A, which equals 2.93. Therefore, the final concentration of P should be the initial concentration plus delta P, which equals, let me see what it was. Which equals 3.13. Okay. Do I have any questions on this? So you might find it helpful to actually write down this equation. Okay. Now let's look at the second order rate law. So it's the same idea as before, except now the rate equals K times A squared. So 1 over A is linear, it turns out. So we graph 1 over A in time, so we get a line. But the important thing to note here is that the half-life is not going to be a constant. The half-life is not a constant, so it's not really useful, so you don't need to know how to calculate that. So we have 1 over A, T equals 1 over A plus KT. Notice we have a plus here, not a minus sign, right? Because on the other ones, we have a minus sign because this should be less than that. But here, because it's 1 over it, so 1 over a big number is a small number, so we have a plus sign here. So can you just write this down? And I don't think we need to really do a problem based on here because this stuff, okay? It's just the same thing as before, really. Okay. So I just want to make a small note on coefficients of a reaction. Oops. So far, we've only considered with the coefficient of 1 because it's easier, but a lot of reactions do not have coefficients of 1. So we have A goes to P, so some amount of product. So if the overall reaction has a rate R, then the rate of consumption of A should be A times R, and the rate of production of P should be P times R, because R describes the rate of the overall reaction. So for example, in this case, if the rate of this whole thing is 5, then the rate of production, the rate of consumption of NO2 should be 10. The rate of production of NO should be 10. And the rate of production of O2 should be 5. Does that make sense? So you can see in the graph here, we can see that NO is being produced twice as fast as oxygen. Right? So, yeah. So you can see that the oxygen is being produced twice as low as the NO, and the NO2 is being consumed twice as fast as the oxygen is being produced. So I'll give you, I don't know, maybe, so I'll give you 10 minutes to do this problem. So the first step is to find the reaction order, which I have not told you. But you can deduce the reaction order from the units. And by the way, you can consider pressure to be the same thing as molarity, okay? So pressure and molarity are basically just you can think of them as the same thing for now, okay? So you need to, oh, I did tell you the order, okay. So the so you should be able to deduce it from the units, but I've given it to you. So I'll give you maybe 5 minutes about, 5 minutes, good? Okay. So I want you to calculate the pressure of NO2, the pressure of NO, and the pressure of oxygen. Anyone remember the first order integrated rate law? The first order integrated rate law. So you can always just look back at your notes, right? And it's very crucial that you record these down at least if you can't remember them, because these will probably show up again and again, right? So can someone just tell me what the first order integrated rate law is? Great. AT equals A0 times e to the negative kt, or in logarithm form. Either form is perfectly useful and acceptable. Okay. So, okay, so I got some new paper. Okay, so what are we given? So, oh, wow, that's my bad. I didn't say the reaction time. Oh, I think I forgot to indicate the reaction time. Okay. Yeah, so next, if you ever think that there's a problem with one of the problems I've written, just please tell me as soon as you can, or else this stuff won't happen. This question is impossible to answer since I have not given the reaction time. Okay, well, just to illustrate a point, let's just go for, let's say 10 seconds. So let's say we react these for 10 seconds. Okay, so, therefore, okay, so then what should we do? Okay, so let's find how much the reaction goes forward overall. Let's look at how the overall integrated rate. So I'm trying to think of a good way to explain this. So, oh, okay, here's a great, okay. So another thing you can do is you can take, so you can multiply, if you want to consider the individual reactants and products individually, you can multiply the rate constant by the coefficient. So we can say that so then we can say that I don't think that works. Wait, let me think for a second. Yeah, this probably is not a good way of doing it. Let me think for a second. So, yeah, because you end up getting some weirdness, because if we do e to the negative 2 kt, then this gets NO2. Squared. All right. Yeah, which I don't think is correct. So I don't think you can really do it legitimately that way. Or, yeah, so let's do it let's do it this way. So we know that this reaction goes forward with K equals 0.02. Okay. So now we can find the change in, okay. So, So let's start with oxygen. So oxygen is the easiest because we have a coefficient of 1. So it's very easy to work with mathematically. So we can say that, so therefore we have that, so here we should, wait, what were the initial values? So we have P of NO2 equals 0.5 atmospheres. Okay. Okay, so I actually do think you can multiply the rate constant by 2. Because, you know, because if you do it this way, right? Like this statement is true. So when you go to do the calculus, it should all work out. So I think we can do it this way. Yeah. So then NO2T equals right. So then we can solve this. So that equals 0.5 0.5 times e to the negative point, what did I say? 0.02 times 2 times, we'll say for 10 seconds, right? Yeah, 10 seconds. Great. So now we've calculated the final pressure of NO2. So therefore we can say that, oh, often you might see pressure as just in parentheses. So parentheses are another way to indicate pressure. So the change in pressure is going to be, and then this equals, so negative 1.64. Wait, negative 1.64 times 10 to the minus 1 atmospheres. Therefore, yeah. So, yeah, okay. So therefore, since we know, so from the equation here, we have that for every 2 moles of NO2 that we consume, we produce 2 moles of NO. So therefore, delta NO equals, also equals 1.64 times 10 to the minus 1 atmospheres. And delta O2 equals delta NO divided by 2, right? Because oxygen is, we're producing half as much oxygen as nitrogen, NO. So this equals 0.082. Okay? Yeah. So a little bit tricky math, I guess. Okay. So now we can talk about mechanisms of chemical reactions. So let's look at the reaction. A plus B goes to C. Okay. Now, this looks deceptively simple, but we don't have to. The reaction mechanism isn't necessarily just one step. We often go through many different steps, which are called elementary steps. So, yeah. So we form these elementary steps, and these elementary steps will often produce intermediates. So intermediate 1, intermediate 2. So unlike the regular one, unlike the regular equation, for an elementary step, we can set the coefficient on the exponent equal to the coefficient in the equation. And this only works for elementary steps. So for example, here, we have a coefficient of 1 here. Therefore, it should be k, some constant times a to the first power. And likewise for these. So here we have a coefficient of 1 here and a coefficient of 1 here. Therefore, we should have a 1 in the exponent and a 1 in the exponent. So, can someone tell me the rate equation for this? What's the rate law for this equation? Can someone tell me the rate law? So remember, the rate law is some kind of expression like this. So I want you to write something like this, but for this reaction. Equals some constant times now, can someone tell me the values of n and y? Now look at this number here and this number here. That should be there. You can imagine a 1 here. I'll rewrite it. So can someone tell me the values of n and y? Great, so n equals 2, y equals 1. So since you can simply move the coefficients into the exponents. Right, and this only works for elementary steps. So for the other, so for this whole thing, you cannot do that, okay? This only works for the elementary steps. Because the rate laws of the elementary steps will overall determine the rate law of the overall reaction. So it's the elementary steps that matter, and the overall reaction depends on the elementary steps. The coefficients on the overall reaction don't actually impact anything. Okay. Now let's look at this example. Okay, so we have A goes to intermediate 1, B goes to intermediate 2, and then intermediate 1 and intermediate 2 go to C. So this is the same as before. So the overall rate will depend on the slowest step, and the overall rate law will also depend on the slowest step. In other words, the reaction with the smallest k. So for example, if K2 is the smallest, the overall rate law will simply be K2 times B. The concentration of A will not impact the overall rate. Okay? So you can, to illustrate this, we have this thing. So we have a big beaker, we have a big funnel, a medium funnel, and a small funnel. So the big funnel can transmit a lot of fluid. The medium funnel has a medium flow rate, and the small funnel has a very slow flow rate. So as you can see, although the medium funnel and the big funnel are not full, the small funnel is limiting the rate that water can be transferred through the system. And it doesn't matter which position it has on the column, the flow of water will always be limited by the small funnel. So there was a kind of like, I remember reading a book, so it had a funny illustration of this. So imagine we have a washer drying machine, so a washing and drying machine. So it will do your laundry. So on the first step, you have a bunch of badly trained, uncooperative weasels who are trained to wash the clothes. And because they are ill-trained and uncooperative, it takes them 24 hours to wash a batch of clothes. For the second component, you have a nuclear-powered oven that can dry your clothes in 1 millisecond. So how long does it take to do one batch of clothes? Well, obviously, the nuclear oven will go much faster than the weasels. It takes up 1 millisecond. So it takes 24 hours to do a batch of clothes because it's limited by the rate that the weasels can wash the clothes. So here we have a problem. So I've given this, we have this reaction, and it's composed of these 4 elementary steps. So I want you to, so find the rate limiting step, and then find what's the rate law for the overall equation, and calculate the concentration of C after 1 minute. And you can, yep. So, so make a rough sketch of the concentrations of all the species versus time if you have a little bit of extra time. So you don't need to do any calculations for this stuff. So 15 minutes, is that okay? So it turns out that, okay, so just when you do it mathematically, because actually, I realized that this is very, very difficult to do without calculus. So let me see, how do we fix this? Okay, I know. I'm gonna edit this real quick. Yeah, I'm glad I caught that. Wait, so how about I write it down on paper? I'll write down an example on paper. Or we can just do actually, I have a better idea. Let's just continue using the same one as before. So A, and I haven't given units. I want you to figure out the units. And let's say, okay, can we do that instead? So, okay, can we do this problem instead? Yeah, that's my bad. So the overall reaction can be found by just adding all of these together. So what is, when we add all of these together, what do we get? So it's just A plus B goes to C, right? Okay. Now, which one is the rate limiting step? 1, 2, or 3? So it's the one with the smallest K, the slowest rate, right? So reaction 1 is much smaller than the others. Great. So we've identified our rate limiting step. So therefore, what should be the rate law? Remember, the rate law is determined by the rate limiting step. So what should it be? That's the rate constant, but what's the rate law, right? Remember, what's the expression that combines the rate constant and the concentrations? The rate constant by itself can't give you the rate. You need concentrations. So what's the rate law? Well, what's the coefficient on A? What's the coefficient on A? 1, right? So rate equals our rate constant times A to the first, right? This is the rate law, okay? It gives you the rate, okay? So can someone tell me what the first order rate law is? Great. So let's just plug in some numbers. So negative 0.05 times 4 minutes. Okay, so then delta equals negative 0.906 molar. So therefore, can someone tell me the concentration of C? What's the concentration of C then? So look at this and this. So this tells us how much of A we've consumed. So if we've consumed 0.906 A, how much C is being produced? So for every mole of A we consume, we produce 1 mole of C. So great. So we've produced 0.906 moles of C. So that's okay. So that's the final concentration of C. Okay. Now let's move on to the second part. This is the interesting part. So graph the concentrations versus time. So I have here 3 pens. So this can be C, this can be A, and this can be B. Okay, so we have 3 steps. Okay, therefore, so look, B does its own thing by itself. So B will decrease very quickly. So something like that. So B will just decrease very quickly. Now, the interesting thing, so because it has a large K, this one is a very small K. Therefore, A will decrease much more slower. Something like that. Now, let's look at the concentration of IA. So I will do IA in purple. So at first, notice how as the concentration of A decreases, we're producing IA. So the concentration of IA should increase. However, when IA increases a lot, then this reaction will start to occur. This reaction will get faster as IA increases. So IA will actually start to settle down. And eventually, all of the intermediate will be consumed. Okay? And the same thing goes for IB, right? So I guess you can imagine that, so IB will at first, I can do IB in red. Okay. So IB will first increase very rapidly, right? Because B is being decreased very rapidly. But then IB will settle down. And they both eventually will decrease. Okay? And finally, we have C. So in black pen. So C starts off as 0. And the production of C depends on B. So, I mean, it depends on A. So therefore, C should basically just follow A. Right? So as A decreases, C is produced. So just want to show you that so often we can have very strange. So basically, my main point here is that the concentration of intermediates is often very low, and it's often relatively stable. You can see that here, our line is pretty flat. So maybe if you do some more advanced chemistry, you'll see how this is important when we talk about like things like steady state approximation. Okay. So one final thing. It's one last topic for now. Let me see how much time we have left. Yeah, we have a good amount of time. I might be able to introduce a little bit of equilibrium, which will be a tie into the next lesson. Okay, so basically, remember as temperature increases, the collisions will start to have more energy since our particles will move faster, right? So we can summarize this using the Arrhenius equation. So Savant Arrhenius was a chemist in like the 1800s. And very interestingly, he actually predicted climate change. So he predicted that the increasing amount of CO2 in the atmosphere would lead to an increase in global temperatures back in the 1800s. So interesting. So here we have the rate constant. Rate constant equals some constant A. So A is some constant times e to the negative EA over RT, where R is the gas constant. So does anyone remember what the gas constant is equal to? So R. What does R equal? Does anyone? Well, I'll just tell you. R equals 8.314. So 0.08206 is when we're working with liters in atmospheres. But here, we're working with activation energy. Activation energy is in joules. So we should use 8.314 joules per mole Kelvin, not liter atmospheres. So R equals 8.314. Okay. And the rest is self-explanatory. So the Kelvin temperature. So we have to convert to kelvins as usual, and the activation energy. So how much energy does it need to have to be a successful collision, which we talked about earlier. Now, I just want to briefly talk about this frequency factor, the pre-exponential factor. It's usually some huge number, and it's basically, it doesn't have too much physical significance. Basically, just it tells you like it depends on factors like orientation or stuff like that, like size and stuff like that. But it's a constant. That's all you need to know. And we also have this equation here. So we've put it into logarithm form. So can everyone write this down? And you might notice that this equation is actually very, very similar to the Clausius-Clapeyron equation. So you don't need to memorize too much stuff, just memorize one thing. Okay. Okay. So has everyone written that down? Written these things down? Okay. So I'll just give you 5 minutes to do this problem. So a chemical reaction will double in rate when we increase the temperature from 25 Celsius to 35 Celsius and calculate the activation energy. So 5 minutes, I think. So let's just go over this. Okay. So we have to use for this, it might be more convenient to use the logarithm form of the Arrhenius equation. Now, can someone tell me what T1 and T2 are? What are T1 and T2? So we're given two temperature points. So what do these become? So everyone remembers how to convert to Kelvin, right? Right. So can someone convert these to Kelvin? You need to add 273. So this should be 298, right? Yep. And then this should be 308 Kelvin. Okay. So we have T1 and T2. Now we're given that the rate doubles. However, we are not given the exact rate constants. But we do know that there is a ratio. So we can say that ln of, so we know that K1 must be 1/2 of K2 since we're given that the temperature doubles, the rate doubles. So this should be 1/2. And would someone like to solve this equation for EA? Can someone solve this? (5.28 times 10 to the 4 joules). Okay. Now, I think we might need more practice with doing the numerical calculations a little bit more quickly. So I think, how about this? Wait, so I'll post the homework and maybe you can try doing it in maybe like 10-minute intervals. So don't spend too much time on the homework, just spend 10 minutes and see what you can get through. And then if you need to, you can spend another 10 minutes and just try it that way. Okay. I think now would be a good time to introduce a new topic. So I will just briefly talk about this. So far, we have only considered reactions that go in one direction. So such a reaction would be called irreversible. However, most reactions are reversible. We can say okay, see, we can have two parts. We call this K1, k minus 1. And then, I don't know if this is immediately intuitive, but at some point, the rate of the forward reaction will equal the rate of the backwards reaction. So I'll put it in another way. And we often draw these types of situations with a double-headed arrow. So k plus 1 and k minus 1. So we have this double-sided arrow. So at some point, the rate of the forward reaction will equal the rate of the reverse reaction. Once this happens, this system can be said to be in a state of dynamic equilibrium. And it's called, this is equilibrium because nothing changes. At that point, the rate of the forward and backwards reaction cancel each other out, so nothing happens. However, there is still movement. A is still getting turned into B, and B is still getting turned into A. It's just that they perfectly cancel each other out. So this is why it's called dynamic. Stuff is still happening. It's not like all the molecules have just stopped. It's just that it balances everything out, okay? So we have that the forward reaction, so K1 equals the reverse reaction. And we'll just assume that these are all elementary steps because it makes everything easier. So we have this expression, and then we can even we can rearrange it to get this. Wait, this should, I'll make it better. B over A. So we can arrange this to get this. We can call this the equilibrium constant, capital K. So let's consider a situation where we have this. Okay, so as you can see, K, the forward reaction and the reverse reaction are very, very fast compared to the second reaction. Therefore, we will achieve a state of equilibrium here. Okay? We will achieve a state of equilibrium. Because this stuff will all even out before any C reacts to form D, before we have a chance to form D. So therefore, we can say, so how do we do this? So we can say that don't worry about units. It should all be fine. Just don't worry about it for now. So then therefore we write okay? And then we can further rearrange this too. Great. Now, I've run out of space. Great. So, some paper here. Okay, so we're almost there. Now, I want you to notice that this rate, K2, right? So this will tell us the formation of D. This is the rate of formation of D. Okay? This will tell us the rate of formation of D. Okay, this equation. But we don't know what C is. But we've just solved it here. So therefore we can say There. So now we have this very nice expression for the formation of D based on A and B. And we will definitely talk about this more in detail next lesson. This is basically all next lesson is going to be about. All of this dynamic equilibrium, these reactions that go forward but also in backwards, so they don't complete. So do I have any questions right now? If not, the lesson is basically about done. So I'll see you later and have a